So now what we want to do is prove some useful lemma. So recall that we have this bad event. Let's write it this way. And we want to know how many of these bad events happen. I mean, it's not necessarily bad event, but some out of these events, we want to know number of B alpha which actually occur. And the case we are dealing with are where dependency is weak. So alpha and beta are related, and delta is measuring this dependency, and we want somehow this to be small. Or, I mean, many cases, these are small in several regions. Either these terms are small or the pair which are related are small. And lots of cases, what actually happen is that instead of just counting all the events that happen, if we list the events which happen and in a way that they are not related, so they are independent. They are independent, and we count this. Then, many cases, number of such events and number of events that actually happen could be not so far. They could be similar. Lots of cases, this actually is the case. Because this delta is probability that B alpha and B beta happen where these two are related, right? And our assumption is that this is quite smaller than mu. In lots of cases, this is the situation that we are dealing with. Then, intuitively, the number of B alpha actually happen is mu, and number of pairs where they are related and that happen together is smaller. So if we just count the events where pairwisely all they are independent and they happen, must be at least mu minus little mu, which is, if this is close to mu, then this upper bound is this, which is close to mu, and lower bound is that minus this delta, which is small. So this count and this count intuitively should be very close. So lots of cases, instead of counting this, if we count number of such events, of course we have to count all. So we have to add the events so that we cannot add any more, so that all the remaining things are somehow related to at least one of them. Then these two should be similar. So, but if you actually do some computation, lots of cases, computing this and computing this might be easier. So, based on this idea, if we prove some lemma on here, and then later we want to transfer, we get some information about this, and based on that, we want to make some conclusion on here. That's what we want to do. For that, let's say we have the previous setup. Give me a moment. So we consider the setup, and we have this random set chosen in this omega, and we call J, which is a collection of indexes, we call this as a disjoint family, and write this PAM if the following holds, that AJ is subset of R for every J. So, meaning that the BJ, J in J, this occur. And the event J and I are independent. Then we say this is a disjoint family. And also, we have one more property in addition to the above two. Then we call J a maximal disjoint family. And write max disfam. So that this is actually maximum, which means that for all J prime outside of J, and if this is an event that occur, B sub J prime is something that occur, then AJ prime and AJ are not, they intersect for some J. So that means if you have this J and we have the corresponding event, and if we have another event which happen where J prime doesn't belong to J, then this has to be related to, this has to be dependent to one of them. So this has to be, not independent to at least one of these events in J. Then we call this max disfam. Then again, mu is the expected number of x. X counts the events that occur. Then the lemma we want to prove is we want to estimate the probability that we have a disfam of certain size or max disfam of certain size. So, with the above setup and on integer s, we have that the probability that there exists a disfam J with size s is at most mu to the s over s factorial. So we want to prove this. So this is not difficult. So we consider all possible disjoint family. So of omega. So when R is omega, when R equals to omega, J is disjoint family, then we consider all such one. And the probability that it actually becomes a disjoint family with a random set R is that if all of the event holds, then it becomes a disjoint family. So we have this. So all possible, J, we add up the probability that it becomes a disjoint family. Then we have this equality. Because J is a family of indices where Bi and Bj are independent. So these events are all mutually independent because AI and AJ are disjoint. And those sets are all, those sets AJ, where J is in J, this forms a pairwise disjoint set. That means they are mutually all disjoint. So B1 to, BI, BJ, where J is J, they form a mutually independent events. So we can just multiply the probability of each event. This is, you just add a additional element of ordering, where J1 to Js are subsets of omega, and J1 and two of them are not. So let's write this in this way. J1 to Js Ji is not related to Ji prime, or I prime not equal in S. So it seems that I didn't specify the size of this J, that's S. I should have specified that. So for all over such a set where no two of them are related, we sum this, the probability that this J actually forms a disjoint family. And this is that. And now we give the ordering. The same J is counted as factorial time. And you multiply them in this way. And you have 1 over S factorial. But what does this term? This term is just upper bounded by, you take all the probability sum, and you take the S's power. You multiply them S time. Then you have this 1, 2, 3, and you choose one term, they multiply together. This gives us a more term, so in here they must be independent, but here actually give an additional term where they are even related. But it's certainly an upper bound. It might give an additional term, but all the terms here are certainly in here. And what's this? This is nothing but the expectation. So this is mu to the S over S factorial. So you get this lemma, which measures the probability that there exists a disjoint family with size S. And if we know that this mu to the S is smaller than S factorial, then this becomes a small probability, so it's useful. And this happens basically when S is bigger than mu times alpha, or some alpha bigger than E. Then you can actually check that this S prime is bigger than mu to the S. Otherwise, if this doesn't happen, then this is become bigger than 1, then it's not so useful. But if S is small, then we can instead consider the max dispam. So in order to estimate the probability of the existence of max dispam with size S, we want to define some term. So let mu sub S be the, let's say, minimum of, we'll choose J1 to Js in I. and you sum so that the S elements are fixed, and then you sum over all I, where I is not related to all of them. So if I is related to at least one of them, we forget it, and then we take the rest of them, we sum up the probability of Pi, then this is mu S. And when we choose this J1 to Js, we choose the one which guarantees this, the smallest. And let's write the nu as the maximum over all J, where you add up all probability of Pi, where I is related to J. So what this means is that we want to add all probability of Pi. If we add all probability of Pi, then we get nu. But we want to subtract the ones which are related to at least one of them. So we want to take out the ones that's related to J1, and so mu of S is at least as large as the following term. This term up until to the I is related to J sub L. J sub S. So there are S terms, and each of these are smaller than nu. So it's not easy to show that this happened. So mu sub S has lower bound, which is mu minus S mu, S nu. So with this, what we can show is the probability that there exists a maximum disjoint family J with size equal to J is upper bounded by nu to the S, S factorial, e to the minus nu S, e to the delta over 2. Again, we use this inequality, then this is nu to the S over S factorial, e to the minus mu plus S nu, e to the delta over 2. So if S nu is small and delta is small, then this is at most mu to the S over S factorial, e to the minus mu, which comes from the Poisson distribution, that the Poisson distribution has a value S. So this can be upper bounded by Poisson distribution if these are small. So that's what we want to prove next time. And then we want to use this to get some results on other problems. And we will see some application of this lemma about the disjoint family and maximum disjoint family.